In computational complexity theory, the PCP theorem, also known as the PCP characterization theorem, states that every decision problem in the NP complexity class has probabilistically checkable proofs that can be checked by a randomized algorithm of constant query complexity and logarithmic randomness complexity, uses a logarithmic number of random bits. The PCP theorem says that for some universal constant k, for every n, any mathematical proof of length n can be rewritten as a different proof of length poly n, that is formally verifiable with 99% accuracy by a randomized algorithm that inspects only k letters of the proof. The PCP theorem is the cornerstone of the theory of computational hardness of approximation, which investigates the inherent difficulty in designing efficient approximation algorithms for various optimization problems. It has been described by Ingo Wegener as the most important result in complexity theory since Cook's theorem, and by Oded Goldreich as a culmination of a sequence of impressive works. Rich in innovative ideas. Formal statement. The PCP theorem states that NP equals PCP O log n O 1 PCP in hardness of approximation. An alternative formulation of the PCP theorem states that the maximum fraction of satisfiable constraints of a constraint satisfaction problem is NP hard to approximate within some constant factor. Formally, for some constants k and alpha less than 1, the following promise problem lies LNO is an NP hard decision problem. Lies equals phi. All constraints in phi are simultaneously satisfiable. LNO equals phi. Every assignment satisfies fewer than an alpha fraction of phi s constraints, where phi is a constraint satisfaction problem over Boolean alphabet with at most k variables per constraint. As a consequence of this theorem, it can be shown that the solutions to many natural optimization problems, including maximum Boolean formula satisfiability, maximum independent setting graphs, and the shortest vector problem for lattices, cannot be approximated efficiently unless p equals np. These results are sometimes also called PCP theorems because they can be viewed as probabilistically checkable proofs for NP with some additional structure. History. The PCP theorem is the culmination of a long line of work on interactive proofs and probabilistically checkable proofs. The first theorem relating standard proofs and probabilistically checkable proofs is the statement that any exp PCP poly n proved by Babai, Fortnau and Lund, 1990. Etymology of the name of PCP theorem. The notation PCPC N S N R N Q N is explained at probabilistically checkable proof. The notation is that of a function that returns a certain complexity class. See the explanation mentioned above. The name of this theorem, the PCP theorem, probably comes either from PCP, meaning probabilistically checkable proof, or from the notation mentioned above, or both. History after the first theorem. In 1990. Subsequently, the methods used in this work were extended by Babai, Lance Fortnau, Levin, and Shajadi in 1991. Babai al. 1991. Fage, Goldwasser, Lund, Safra, and Shajadi, 1991, and Aurora and Safra in 1992. Aurora and Safra 1992. To yield a proof of the PCP theorem by Aurora, Lund, Motwani, Sudan, and Shajadi in 1998. Aurora al. 1998. The 2001 Gödel Prize was awarded to Sanjeev Arora, Uriel Fage, Shafi Goldwasser, Karsten Lund, Laszlo Lovis, Rajiv Motwani, Shmuel Safra, Madhu Sudan, and Mario Shajadi for work on the PCP theorem and its connection to hardness of approximation. In 2005, Wegener discovered a different proof of the PCP theorem using expander graphs, quantum analog of the PCP theorem. In 2012, Thomas Vidic and Tsuyoshi Ito published a result that showed a strong limitation on the ability of entangled provers to collude in a multiplayer game. Quote, "This could be a step toward proving the quantum analog of the PCP theorem." Since when the result was reported in the media, Professor Dorota Aharonov called it the quantum analog of an earlier paper on multi-prover interactive proofs that basically led to the PCP theorem. Notes: Arora, Sanjeev, Lund, Karsten, Motwani, Rajiv, Sudan, Madhu, Shajadi, Mario, 1998. Proof verification and the hardness of approximation problems. Journal of the ACM. 45. 3. 501 to 555. DOI. 10.1145 278,298.278,306. Arora, Sanjeev, Safra, Shmuel, 1992. Approximating cliques NP complete. In Proceedings of the 33rd IEEE Symposium on Foundations on Computer Science. 41. 1. 2-13. Arora, Sanjeev, Safra, Shmuel, 1998. Probabilistic checking of proofs. A new characterization of NP. Journal of the ACM. 45. 1. 70-122. DOI. 10.1145 273,865.273,901. Babai, Laszlo, Fortnow, Lance, Levin, Leonid, Shajadi, Mario, 1991. Checking computations in polylogarithmic time. STOC, 91. Proceedings of the 23rd Annual ACM Symposium on Theory of Computing. ACM. pp. 21-32. ISBN 978-089791-397-3. Babai, Laszlo, Fortnow, Lance, Lund, Karsten. 1990. Non-deterministic exponential time has two prover interactive protocols. SFCS, 90. Proceedings of the 31st Annual Symposium on Foundations of Computer Science. IEEE Computer Society. pp. 16-25. ISBN 978-0818620829. Dinner, Irat. 2007. The PCP Theorem by Gap Amplification. Journal of the ACM. 54. 3. 12. DOI. 10.1145 1,236,457.1,236,459. Fage, Uriel, Goldwasser, Shafi, Lovis, Laszlo, Safra, Shmuel, Shajadi, Mario, 1996. Interactive Proofs and the Hardness of Approximating Cliques. PDF. Journal of the ACM. ACM. 43. 2. 268-292. ISSN 0004-5411. DOI. 10.1145 226,643.226,652.